from 41 through 50, or it could be the older stuff too. That's okay still also. Hi, Alex. 18. Sure. I guess we should type something in here. What's today? The 26th? Okay. So 18, we're given some points. Okay, and in number 18, we wanted to find -5 times the vector CB plus the square root of 2 times the vector BD. So the first thing I'm going to do is calculate or write the vector CB and the vector BD in component form. So that's going to be using the head minus tail rule. So the head is the B, so I'm going to do 5 minus -2, and then -4 minus 9. And then same thing with BD, so I'm going to do -1 minus 5, and then 6 minus -4. So far, so good? Order of operations says next thing I should do is the scalar multiplication. So that's -35, and then positive 65. And then I can't multiply a radical and a whole number together, a rational number together. So I just have to write them like next to each other like that. So far, so good? And then we add vectors, and I can't add a radical with a rational number, so I just got to kind of like write them next to each other like that, and that's as good as we can probably do. Is that okay? Okay. Katie? 26. So it asks us to prove the distributive property. So what I'm going to do is I'm just going to start by defining each of my 3 vectors in component form. And what I'm going to do is I'm just going to start on the left-hand side and try to work till I get to the right-hand side. So I'm going to start by just rewriting the vectors inside the parenthesis in component form. And to do that vector addition, I add the first components together and then add the second components together. And now I'm going to rewrite y or w in component form also. So far, so good? Okay. I do my definition of a dot product. So u1 plus v1, that's the first component, times w1, plus u2 plus v2 times w2. So that's just the definition of my dot product. And then let's distribute those w's through. So I have u1 w1 plus v1 w1 plus u2 w2 plus v2 w2. Notice at no point here do I have a vector anymore, right? These are all just real numbers. So I can regroup them in any way I'd like. So I'm going to put the stuff with the U's together first, and the stuff with the V's together second. And it's okay to do that because these, again, are just real numbers, so I can add them in any order I want and group them together to do the addition in the order I want. If I look at this first quantity, though, that's the definition of a dot product between vector u and w. And if I look at the second quantity, that's the definition of a dot product between v and w, which is exactly where I was trying to get to. Does that feel okay? So all of these, all those dot product proofs essentially come down to the same thing. You're just putting them in component form, pushing through the definitions, and then to get what you need out of it. Who's next? Nat?
Number 28.
Okay. So u dot u is equal to the magnitude of u squared. So again, same setup. I'm just going to start by defining u in component form. And we're just going to start on the left and keep going until we get the right. So I'm just going to start by rewriting my vector u into component form. I'm going to use my definition of a dot product. Now u1 times u1, that's just a real number, so I can write as u1 squared. Similarly with u2 times u2, it can just be u2 squared. So far, so good? Now, what I'm going to do is I'm going to put a square root over top of this with a squared outside of the square root. And it's okay to do that because that's doing nothing at all, particularly if the u1 squared and u2 squared, since they're squared, they have to be positive numbers anyway, so like totally fine to put the square root over top of that. Good with that? And the reason I want to do that is because this part is the definition for the magnitude of u. And I'm done. Sure. So the sneaky part there was doing the square root and the squared outside of it. Mm-hmm.
Number 38.
The same way you do 37.
It's pretty on point, yeah, but I couldn't figure out either of them.
So you're just using the angle between two vectors formulas. So if I go and plot this thing, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. So we have negative 2, 1. And then we have negative 8, negative 4. And then we have 5, 7. So I guess it kind of, that's kind of our triangle then, I guess. Oops, that's y, that's x, that's 7. So it's pretty flat, but if you drew it in like a super accurate space, it's not completely flat. So what I'm going to do is I'm going to find these two vectors and the angle between them. And then say these two vectors and the angle between them. And then I can get the third angle for free.
Okay, so but when you're finding that triangle, the gray vector, isn't that just the same thing as the red vector?
Well, no, it's the opposite direction. It has the same length, but it's not the same vector.
Okay, you're right.
So we'll start here. So the first ones I need YZ, and then YX, and then I need XY and XZ. So when I do YZ, I'm going to do Z minus Y, so that's 13. And then Z minus Y, so that's 11. And YX, so that's going to be X minus Y, so that's positive 6. And X minus Y, so that's 5. X minus Y, so that's Y minus X, so that's negative 6, and well, negative 5, clearly. XZ is going to be Z minus X, so that's 7, and then Z minus X, that's 6. So the angle between these two vectors is going to be the dot product of the two vectors divided by the magnitude of the first vector times the magnitude of the second vector. So let's see, 13 times 6 is 78. And then 11 times 5 is 55. 13 squared plus 11 squared is 290. And 6 squared plus 5 squared is 36 plus 20, so 61. So 0.43 degrees. I mean, that didn't seem absurd based on our picture. Notice that along the way, we also got the side length for YZ and the side length for YX. So I'm not going to bother to separate those out because they're right there. And then I do the same thing over here for this one. So we have negative 6 times 7 plus negative 5 times 6 over the magnitude of xy is still the same thing as the magnitude of yx, so I already have that. And then I have 7 squared plus 6 squared, so 49 plus 36 is 85. I think that'll do it. Here again, especially this problem, because the angles are so small or so big, you'd really get punished if you probably rounded those square roots. It's very likely you could throw an error because just a little bit of rounding might give you something outside of the domain of cosine inverse. So you'd want to be very careful there to use the radicals. So I get 179.20. And I guess, what is it? That's angle X. This is angle Y. And again, to point out too here is that's our angle XZ. So that's our third side, excuse me. And then our angle Z is just going to be the leftovers. So 180 minus the previous minus the 0.43. So 0.37.
I did most of that, but I just, like I said, wow, those are tiny angles. I'm doing this wrong.
No, if you looked at the picture, you've been like, well, I guess that's not absurd. The picture is almost a straight line. So the picture really helped in that case.
It did, yeah. I didn't draw a very accurate picture.
Yeah,
it's
to
just
just
a triangle on a graph.
Nat.
Could you technically use the law of cosines for this problem?
Sure. Yeah, if you got the side lengths, you could use law of cosines after you calculated the side lengths.
So I did that, but I thought there's no way it's 179.
Yeah, no, that's not a terrible method either. Certainly doable, especially with what you had from last chapter. The idea was, and again, this angle between two vectors is basically law of cosines. As I bet if we worked out the numbers between the two, you'd end up with the exact same thing. You're taking the cosine inverse. I mean, you should, but Alyssa?
49, please.
49. Oh, yes, of course. Okay. I'm going to just copy this one in, I think, from the numbers, because I don't want to write down all those words. What about you guys? Yeah, pass on that. All right. A crate weighing 50 pounds is IBIS. That's like what it's probably supposed to be. Is being pulled up a ramp at an angle of elevation of 48 degrees with a force of 150 pounds. The ramp has an angle of elevation of 35 degrees. What is the amount of force being directed up the ramp? When we read this question, what is different about this question than any of the previous ones we've looked at?
The crate does not have a negligible weight.
Yeah, the crate has a weight this time. So what's that really telling me? Is I really have three vectors going on here instead of just two. So there's two vectors that are being directed into the ramp. There's the vector for the gravity on the crate, and there's the vector pulling the crate up the ramp. Is that okay? So just to draw those in, here's my vector for the gravity on the ramp. I'll call that G. This is the vector pulling on the crate. I'll call that vector P. And then we have the ramp itself. I'll call that vector R. So the magnitude of G, we're told, is 50 pounds. And the angle for G, well, that's clearly just 270. The magnitude on P is 150. And our angle for P, well, that's just got to be 48 degrees. Our magnitude for R should be, are we told how long the ramp is? No, so what do?
That's just a variable.
We're going to assume it's 1. Make it a unit vector. Makes it easier to deal with. And the direction for that ramp then will be 35 degrees. Now, what I want here is really the projection of P plus G onto R. So I'm going to start by resolving everything into component form, adding vectors P and G, and then projecting that resultant onto R. So start by putting these into component form. Okay. Now, really what we want for this problem is the magnitude of the projection of P plus G onto R, right? Now, since R is a unit vector, this really just becomes the magnitude of, or I should say the absolute value of P plus G dot R. So let's just do that on our calculator. So actually, I guess we'll do an intermediate step or two here rather than just going straight through. So did that. So I have 100.37 and 111.47. So that's 0.819 and, well, let's call it just 0.82 and 0.57. So when I do the dot product, should get that. So do that on our calculator. So 117.47. We should probably say up the ramp or something. So that one was a little tricky because you had to add that third vector there, and you had to figure out what the heck do I do with the third vector. Now, you could have done this separately and projected both of them onto the vector. You'd have to be a little bit careful because one of them, the force would be going up the ramp, and the other, the force is going down the ramp. So you'd have had to subtract them. To me, it makes much more sense just to add the two vectors for P and G and then do the projection onto that resultant vector. Because then you don't have to muck around with like, oh, the pull is going up the ramp, but gravity's pulling back down the ramp, so I need to subtract the, you know, like that to me is like, I'd rather not live in that world where I have to like think too intuitively about what's actually physically happening. Like if I just do the vector addition, I don't have to worry about that piece at all because the signs took care of themselves when I added the two vectors. So you have to be a little bit careful there. Nat?
Can you see number 41?
Sure. Alyssa, this was your question. Are you happy with what we did there?
Yep.
Okay. You're welcome. 41. And I think 50 is the same kind of problem as 49. So if you can do 49, you can do 50 the same way. Yeah. So 41 asks us to project vector u onto vector v. So our formula is the dot product of u and v divided by the magnitude of v squared times vector v. So in our problem, u is the vector -3, 8, and v is the vector 7, 2. So that's going to be, the dot product is -3 times 7 plus 8 times 2. The magnitude of v squared, that's 49 plus 4. And I didn't worry about the squared because the square root over the magnitude is just going to cancel with the squared. And then times that vector, 7 over 2. So let's see, we have, that's -21 plus 16, so that's -5 over 53 times 7 over 2. So when I multiply those in, I got -35 over 53, -10 over 53. Nat, does that feel okay? Good, good. Yep. Okay, so I had the magnitude squared. So I just canceled them, you know. It's okay. It's a good question. So again, the magnitude squared is just, you know. I mean, you can draw both of them in. You know, they're going to cancel each other out or whatever eventually. Me, I just don't bother with it. You know what I mean? Just like less writing or whatever. But again, it's first time doing this stuff. So like, write them in if it helps. You know, Blake?
So going back to number 49,
yeah.
What was that formula, like the last formula that you used? What's that called?
Well, this was a special case that we saw yesterday. So if we go back and look, I guess we should have put an absolute value here. But we proved this yesterday, that if u is a unit vector, then the projection of v onto u is just the dot product of u and v.
And since that there was a third.
So for us on 49, the point of it is that we're projecting onto the ramp, which is a unit vector.
Yeah.
which is why I was able to take that shortcut.
Gotcha, okay.
You could have done it the long way. You'll still get the same answer, just more
long.
stuff,
Yeah.
which, you know, like I love that shortcut because oftentimes in real life, you're projecting onto unit vectors. So just like it just saves some time, you know. Alyssa?
For 37 and 38, once you got to like once you found the length function, what was that equation that you used with like the
That's just the angle between two vectors formula. Where did that go? For 38. This piece here is the angle between two vectors. That was in section 8.2, I believe. Yeah, no problem. It's like one of the last things we did in 8.2. Alex, I see your hand. 20. So here we ask, find the unit vector in the same direction as the indicated vector, write it in component form as well as linear combination form. So here's my vector. My formula for a unit vector in the same direction is 1 over the magnitude of v times v. So negative 10 squared plus 3 squared is 109. So I multiply that in. And then I guess I'd probably rationalize my denominator here because this is going to be a final answer. So that's my answer to part A. That's my component form answer. Part B asks for the linear combination form answer. The linear combination form is just the IJ notation. So all I do is I just take the x component and put that on the coefficient of I, and the y component is just going to be my coefficient on j. That's that. Sure. Emily? $32. So we have 3w plus 2u dot negative 4v, where my vector w is negative 2i plus 3j. My vector u is negative 4, 5. And my vector v is, oops, my vector u is not that. My vector u is 3, negative 8. My vector v is negative 4, 5. So first thing I would do is I'm going to convert my linear combination form vector w into a component form. And then I'm just going to do the scalar multiplications first. So 3w becomes negative 6, 9. And then 2u becomes 6, negative 16. And then negative 4v becomes 16, negative 20. I'm just going to add these two vectors together. So that gives me 0, negative 7. And then I'll do the dot product. So I multiply the x components and multiply the y components. And that gives me 140. Is that okay? Jillian?
How did you choose vector W from the 2I, 3J form to the component form?
Yeah, so the coefficient on the I is the x component. The coefficient on the j is the y component.
Oh, that's all that.
That's Well, I is just the vector 1, 0,
Oh,
and j is the vector 0, 1. So when I add those two things together, literally the coefficient on the I just becomes the x, the coefficient on the, you know what I mean?
yeah, that makes sense.
Cool.
Also, would the angle between two vectors be the formula that be on the test, or do you have to memorize that?
That's a good question. I don't remember off the top of my head. I'm going to get the review up here in the next day or two, and I'll put everything that I'm going to put on the test on the review. So the last page of the review has the formulas that I would give you on the test. My suspicion is yes, that's one that I would give you. But I need to look at what I've done in the past to double check that. I think the basic vector operations are things that I expect you to have, like converting back and forth between the different forms and, you know, vector addition or scalar multiplication, that kind of jazz. But my suspicion is that angle between two vectors and like the projection formula are probably things that I would give you. But I'd need to double check my stuff before I can guarantee that. But I'll have it up soon, and that's the best place to check. It's just what's on the last page of the review shows the equations that I would give you for the test. Okay. You guys ready to move forward here? We can always come back and take more questions later, but we've done a bunch. So today we're going to look at section 8.4. Which is titled Vectors in Space. Right, it sounds like a cartoon or something. So right off the bat, we're going to introduce another way to represent a vector. So another form. So our textbook is calling this like the IB component form. In my mathematics education, we'd have called this a column vector. So this is our component form. And that's our IB component form. Or I'll probably slip and refer to this as a column vector routinely. We call it a column vector because like, it's in a column. It's basically the same thing as like a 2x1 matrix. You could treat it the same way there. So if you took a course on linear algebra where you're doing algebra with matrices, this column vectors come up, or column matrices come up a lot. They're quite useful. Okay. So everybody okay with that? It's real simple. There's nothing to it, right? That's the way to go from component form to the column vector back to component form. So the top is the x and the bottom is the y. Woo! Tricky. But it's like, you know, Mr. Kulik, the last thing I need is another frickin' name for a form of vectors. Thanks. Sorry. There's like 6 of them now. I know. This is one of the things that gets confusing about this chapter, is it just gets to be like a lot of names. None of them are hard, but keeping them straight is like, okay, this is now getting kind of a hassle because they all kind of sound the same. Okay. So one of the reasons that we introduced this new notation here is we're going to start writing vector equations for lines. And hi, come on in. Oh, she's right here. Yeah, no problem. Is we're going to start writing vector equations for lines. And one of the things we really want to make sure that we're able to do is keep track between what's a point and what's a vector. And the vertical notation here makes it much, much easier to keep a vector and a point straight. So this is the major reason why we're introducing this other notation right now. is because it makes life a little bit more clear when we start writing equations for a line and we're dealing with points and vectors in the same problem frequently. All right, so let's kind of start talking about how we're going to go about constructing this vector equation for a line. So let's just say we have the slope-intercept equation like 1/2 x plus 1, or y equals 1/2 x plus 1. So if I were to graph this, we have like, a line like this. It's got a positive slope, not very steep, passes through the point 0, 1, whatever. So if I wanted to, we can pick any point on this line, right? There's infinitely many points on this line. Let's say we pick one. Let's say, for example, I pick the point 2, 2. Everybody cool with 2, 2 being a point on the line? Okay. And what I'm going to do then is I'm going to find a vector that has 2, 2 as a as like the initial point on the vector, and is in the same direction as our line. And I could really angle the vector either way, right? And it's still going to be the vector covering that line, whether I'm going to the left or to the right. We're really still talking about almost the exact same vector, they just have opposite directions. So just like a negative sign difference between them, but they're both would equally represent this line. Everybody okay that? Now, keep in mind, when I write this vector, what I really am using is its magnitude and direction. So the point that I'm picking on my line as my initial point doesn't really matter, right? All I need is a magnitude and a direction to describe my vector. So instead of being specific here, I'm going to just call this point like P naught. So I'm going to use a P with a subscript of 0 to describe that point, because I'm going to start being arbitrary now that we've established that, like, yeah, we can pick a point anywhere on here, and I can use that point as like the origin of my vector, and the vector can kind of go either direction along the line. It doesn't really matter. So we have some point. The other piece that we're going to need is the direction of the line. What attribute of our line do you think is going to serve as a proxy for direction? What piece of information about the line is going to be the same thing as our direction? There's only so much information you can say about a line. The slope. Yeah. So note here that the slope of my equation is, or my line is 1/2. Remember that when I find slope, that is the change in y over the change in x. You guys remember that from way back in middle school or some other time? So my direction vector for my vector equation for my line, I'm going to use v to represent that. And my direction vector would be the vector 2, 1 in this case. Why would it be 2, 1? Because the x should be on top in our vector and the y should be on bottom. So that's just looks kind of like the reciprocal of slope. Keep in mind that's not 1/2 or 2/1. That's the vector 2, 1, not the number the fraction 2/1. Very easy to want to stick a fraction bar in there. Please don't do that. That makes things a mess. Because all of a sudden you have a number where a vector should be. You know what I mean? Okay. So then we could say, okay, well, then my vector equation would just be like y equals p naught plus v, right? No. What's wrong with this? Well, I have a vector plus not a vector equals not a vector. There's a whole lot wrong with that statement, right? You can't add vectors and non-vectors. And if I add a vector and non-vector, I should not be getting a real number back. Certainly, I want a vector equation, right? So the equation should be a vector also. So what we do is instead of calling P a point, we're going to call it a point vector. Everybody's okay with that? All right. So one more problem, though. If v is just the vector 2, 1, like I'm limited and I couldn't get, say, like a point way out here or a point way down there on my vector line, right? Because literally 2, 1 plus some point 2, 2 or whatever is not going to give me, I need to be able to generate all the points on this line. So what we do is we're going to include an extra scalar. We're going to use the variable t to represent that any scalar. I know if I multiply a vector by a scalar, it's not going to change the direction of the vector. So it's okay to do this. And now, with this extra parameter t, I can scale vector v to be as long as I need it to be so I can cover anything on the line. Okay. So one more small change, and this is purely notational so that it's not confusing. So instead of writing this as y equals p naught plus vt, we write it as r equals r naught plus vt. So we're instead of using y and p naught, we're going to use r and r naught. Mostly just to help us separate what's an equation for a line versus the vector equation for a line. We're going to use different letters so we don't end up getting confused along the way. So let's just do a quick example, because this is a pretty easy process now that we've kind of laid the foundation. So my vector equation for a line, again, is this. So there's two things that I'm going to need. I'm going to need r naught and I'm going to need v. Everybody's okay with that? R naught is a point vector. So any point on the line y equals 3x plus 5 would be satisfactory to use for our point vector. I'm going to use the y-intercept. My direction vector, well, let's say that's the point, is going to come from the slope. In this case, the slope is 3/1. So my direction vector should be 1, 3. So there's my vector line equation. Mr. Kulik, that's a joke. Yeah, I mean, there's not much to this particular piece. You just have to be able to, like, pull some pieces of information from your equation for a line and then turn them into vectors and plug them back into the formula. None of that stuff was complicated. It's just more notation to remember. What's a little bit more difficult is to take a vector line equation and put it back into slope-intercept form. Did you get your
I
tickets?
got the meet and greet tickets.
Oh, good.
Let's go. That took 10 minutes, but it was worth it.
Okay. All right. So the slope-intercept form needs two things to be able to write the slope-intercept form equation for a line. You need either 2 points on the line or a point and a slope. Everybody agree? What's going to be the easiest two things to get for us? Point and a slope. So my point is going to be 3, -1. And my slope is going to be 3/2. Everybody feel good with that? So I can say y equals mx plus b. So I have -1 is equal to 3/2 times 3 plus b. So that's 9/2. I subtract 9/2 from both sides. I get -11/2 for b. So y equals 3x minus 11/2. No big deal. Feel okay? Last thing we're going to do today is going to be to find the intersection between these two vector line equations. Now, as an aside here, you could definitely just take each of these two vector line equations, convert them to slope-intercept equations, and find the intersection like what you would have done in your Algebra 2 class. It's fine to do that. But I would prefer that we practice doing it inside of the vector form, because in future sections, this technique that we're using with vectors comes back again. So this is a nice kind of precursor to something we're going to build on, or is going to be part of another subroutine. So we would want to be able to do this using the vector form and not just like turn into y-intercept form and do it that way. Okay with that? So I recognize you could do that, and it's fine to do that for this problem, but we do want to learn how to do the vector way because it becomes an important piece of future problems. Okay? Okay, so what we're saying is if I have a point on the intersection of the two lines, is that I have some point x or some point xy that is on this vector line, and the same point xy should be on this vector line. Everybody agree with that? So if I add, or I say do the scalar multiplication and then add the two vectors on the right-hand side here, I'd get 2 plus 1s and then 4 plus 3s. Everybody agree with that? And similarly down here, so really I can say that x has to equal 2 plus 1s, and x has to equal negative 1 plus 3t. Everybody agree with that? So I can say 2 plus 1s has to equal negative 1 plus 3t. And I can do the same thing then for the y's, that y has to equal 4s, or 4 plus 3s, and y also has to equal 5 plus 5t. Everybody's okay with this? And these two values for s and t have to happen simultaneously, right? That both these equations have to be satisfied at the same time by the same values of s and t. So what we formed here is a system of two equations, right? Okay. What I'm going to do is I'm going to rearrange this system so that these linear equations are in standard form. So I'm going to subtract the 3t over and then subtract the 2 over. And then in the second equation, I'm going to subtract the 5t over and then subtract the 4 over, which gives me a system of two equations kind of in that standard form that we're used to seeing. Everybody's okay here? From your Algebra 2 class, what was the fastest way to solve a system of two equations? Or the fastest and easiest? What? I think that we talked about a faster method than that in my class. I'm going to use a matrix and do row reduced echelon form. Did you say that's boring?
Yeah, it's not as cool as doing it.
I mean, I could make you do the elimination by hand if you'd like. Yeah, it's a hassle. It's just the Gauss-Jordan elimination algorithm that the calculator's doing. You could certainly do it by hand. It's not beyond your capabilities. It's just like a hassle. I guess I just bulldozed through this. Do you guys remember how to do this?
Not on the calculator.
Okay. All right, let's just go back and, yes, sure. Okay, so first thing I'm going to do on my calculator is I'm going to open up the matrix menu by pressing second and the x to the negative 1 button. To enter a matrix into my calculator, I'm going to move over to the Edit tab, and I'll pick any matrix. I've picked matrix A. The first thing I'll do is set the dimensions of matrix A. So our matrix is going to have 2 rows, 1 row for each equation, and then 3 columns, 1 column for S, 1 column for T, and 1 column for the answers. And then I type in my matrix exactly as it looks like on my sheet of paper with just the coefficients. So I typed in 1, -3, -3, and my second row is 3, -5, +1. Everybody's okay with that? Okay. I'm going to exit out of here to the main screen, go back to my matrix menu, this time going over to my math tab. I'm going to scroll all the way down to the bottom and look for the command RREF. Make sure you pick RREF and not just REF. And then I'm going to perform RREF, that's row reduced echelon form is what that stands for, on our matrix A that we just created. So I'll go back to the matrix menu. From the names tab, I'll select matrix A, and then just press enter. So this matrix gives me my answer. It says that 1s plus 0t is equal to 4.5, so s is 4.5. And 0s plus 1t equals 2.5. Or if you wanted to, you could use like the fraction command and ask it to give it to you in fractions, 9/2 and 5/2. That's fine also. So just let me write this down. We did RREF on 1, -3, -3, 3, -5, 1. And that gave us 1, 0, 9/2, 0, 1, and then 5/2. So that tells me S is either 9/2 or that T was equal to 5/2. Either one of those is going to be fine to use. So let's say, for example, we're going to use S. All I'm going to do now is go back to my vector equation for the line that includes the S parameter. And perform the simplification. That's 4, so 13/2. And that's 8, so 35/2. So here's your your point of intersection then.
Mr. Collector, any screws end up showing up late to your class?
She has not been here at any point in this
I just
period.
needed to make sure she didn't get marked absent in her first class, so. Okay, thanks.
No problem. So there is my intersection. Jillian?
Oh, softball.
It's okay. Certainly, if you think I make a typo, you should let me know. I don't want to make mistakes, but, you know, best laid plans of mice and men and all that. Well, mice anyways. So again, this, if we take a look at this process, you're probably thinking that seems way worse than just like turning these into slope-intercept equations and solving. Here's where it's not worse, is, well, if you're dealing with something that's not two-dimensional, or if something's like n-dimensional, this becomes much better the bigger the dimension gets. The process that we've just shown you scales really nicely as opposed to doing it by hand with slope-intercept equations that are like, oh, there aren't any slope-intercept equations in 3 dimensions. What the heck does that even mean? So that is the one of the reasons. And the second reason is that this same process of doing what we're doing comes up again in, like, when we talk about parametric equations and parametric functions later on. The same techniques kind of come up over and over again, so it's nice to kind of see it a couple of times. We're stopping here for today. This felt like, again, enough. So I think at this point you guys could now do, let me look at my stuff here. Probably up through 76 now. But let's think about where I want to put that. Probably should put that in the next problem set, not Sunday's problem set, don't you think? Yeah, let's do that. So what's that next date? 2/6.
Yeah, now. Go girl.
Okay, now, I'm going to alphabetical class again.
One last thing to say. We had warned you earlier this week to probably there's a problem or a homework quiz coming soon. Didn't happen today. So you think the odds probably go up for next class?
No. What lessons would it be probably?
So at this point, I would say it would be fair to ask up through section 3.
Okay.
Nothing that we did today, but the previous 3 sections I think would be fair game. Would not necessarily have to include all 3 of those sections, but if you're up through 50 in the homework set, you should be good for next time.
Would you give us equations or no?
I would give you, for example, I'd give you like the projection
Okay.
or the angle between 2 vectors.
Okay.
But like the converting in between the forms, I wouldn't give you that.
Okay.
Like magnitude or direction, like stuff like that, I wouldn't give to you.
Okay, so first I just know that, but if, okay.
And the names of the vector forms you definitely would want to know, since most of sections 1 and 2 is converting back and forth between the forms.
Okay. That makes life easier.
Yeah, and like the vector operations, like addition, subtraction, scalar multiplication, dot product, those are things you should be able to, you should know how to do without a formula. But those are all easy calculations. There's nothing complicated going on there. Does that feel fair?